Hello everyone, good evening guys. So please tell me whether my audio and video is clear or not. Okay, so it's clear from my side. Okay, so my audio and video is clear from my side. I hope it's clear from your side as well. Good evening Sweta, good evening everyone. So now in this session we will discuss about gain margin and phase margin using root locus. Okay, everyone know about gain margin and phase margin from polar plot. Okay, so we'll revise that and then we will try to compare it with the root locus. Okay, so let's first cover the introduction part and then we will start gain margin and phase margin using root locus. So it has actually two parts. In part 1 I am telling you about the gain margin, and in part 2 I will tell you about the phase margin. Part 2 is on tomorrow. Okay, so this is half an hour session and I hope you will understand this concept. So this is a conceptual lecture. In the next class, which is on tomorrow, I will take some questions also so that you can understand this concept properly. Okay, so let's first cover the introduction part. This is my introduction. My name is Asu Jangra and I teach almost every subject. You can start your preparation with me on BYJU'S exam prep platform. There is one free workshop, you can say a scholarship test, so national scholarship test for GATE exam, and that will be on 18th of June at 12 p.m. So you can register now if you are financially, you are not that much strong, or if you want some financial support from BYJU'S exam prep. So you can join this, I mean you can give this scholarship test, and if your marks are good, you can get the scholarship up to 90%. Okay, so that's a good chance guys. You can register now. The link is given in the description. There is a free workshop which will be there on 20th June at 7:30 p.m. and this workshop will be how to ace GATE in 8 months. So this is very important workshop. So you can join this workshop with Rakesh Talleja sir, and this will be at 7:30 p.m. on 20th June. You can register for this free workshop. Link is given in the description. Okay, you can also Guru Dakshina. Okay, so you have to subscribe our channel and press the like button and press the bell icon also, so that you get the notification whenever my sessions are live. Okay, so let's begin our session and let me tell you about the gain margin using a root locus. Now you can see that GSHS is provided to us. Okay, this is our GSHS, K divided by S into S plus 1 S plus 2. And if I plot the root locus, you know that the pole will lie at 0, -1 and -2. For k equal to 0, the closed loop system pole will lie at these points. And if I vary k, then this will be the part of the root locus. This side will be the part of root locus. This side will also be the part of root locus. And the root locus will go like this. Okay, it will go like so. This will be the root locus. We know that. For k equal to 6. For k equal to 6, the closed loop pole will lie at this position. These two pole will lie at these two positions, and this pole will lie somewhere on this side. Okay, for k equal to 6. For k equal to 6, system will become marginally stable. Okay, for k equal to 6, system will become marginally stable. I hope it is clear. Now let's first come to the polar plot also, so that we can compare these two. So we know the root locus of this system, and if you know the polar plot, so the polar plot for GSHS equal to, now GSHS is given as K divided by S into S plus 1 S plus 2. This is my GSHS, and the polar plot for this system is given as this. This is the polar plot, and on polar plot, as you know, omega varies from 0 to infinity. Okay, so omega varies from 0 to infinity and plot will look like this. Now this is the point where the phase of this system will become 180. At this point the phase will become 180, and at this point the frequency, we call it omega PC, phase crossover frequency, it will become √2. You can calculate from the phase criteria the frequency at which the phase become -180. That frequency is known as omega PC, phase crossover frequency, and for this system it came out to be √2. You can check it. Okay, I don't want to go into the calculation part because everybody know how to calculate the phase crossover frequency. This is the polar plot, and at this point k is the distance is k by 6, minus k by 6. Now let's say the question is, if k is equal to maybe let's take k as 2. If k is equal to 2, find gain margin. Find gain margin. Let's say this is the question. We need to find gain margin for k equal to 2. So everybody know how to calculate gain margin from the polar plot. And then we'll go for the go with the root locus also, and we will see how to calculate gain margin using root locus. But first, polar plot. We know that if k value is 2, then this point will be at -1/3. This point will be -1/3. And here you will get -1. Here it is -1. Now from polar plot, everybody know how to calculate gain margin. This length is known as A. This length is known as A. A is this length, okay? And length is always taken as positive. So A value came out to be 1/3. A value is this length. So I will take the positive value. Now the gain margin is, you know that 20 log 1/A. This much of dB. Okay, you can write it like this, 20 log 1/A is the A is 1/3, so you can put the value of A, it will become 20 log 3 dB. So this is the gain margin of the system. This is the gain margin of the system, but this gain margin I have calculated using polar plot. Now, how can I calculate the gain margin for k equal to 2? For k equal to 2, I need to find gain margin using root locus. Let's say the root locus is provided to you, and for k equal to 2, I need to calculate the gain margin. Okay, how to calculate the gain margin from root locus? Let me tell you guys, if you are moving on the polar plot, let's say, if you are moving on the polar plot, it means you are wearing omega only. Okay, you are moving only omega. Now, if you look at this axis, on this axis, we know that S equal to sigma plus j omega. But on this axis, if you look at the imaginary axis, sigma is 0. On imaginary axis, sigma is 0. It means on this axis, only omega is varying. So it means if you are moving on polar plot, it means you are varying only omega. You can see that on polar plot, omega is variable. So if you are moving from 0 to infinity on root locus, you are moving on this axis. So on this axis, only one point lies on the root locus. This point lies on the root locus. If you are moving omega from 0 to omega to infinity, omega from 0 to omega tends to infinity, okay? If you are moving from 0 to infinity, it means on root locus you are moving on this axis. And on this axis, only one point lies on the root locus. At this point, the frequency of oscillation is j root 2. The frequency of oscillation is j root 2. You can calculate using Routh criteria. This is j root 2. Now this root 2 is known as omega pc. It means from the root locus, you know that at this point, whatever this point is, that point is represented by j2, it's the so from here you can calculate omega pc. So omega pc will be equal to root 2. It means the point where the closed loop system become oscillatory, or the closed loop system become marginally stable, that point will give you omega pc. So from root locus you can calculate omega pc. Why I am calling this as omega pc? Because I know that on root locus Ivan conditions are satisfied. What are Ivan conditions? Ivan conditions are magnitude of GSHS equal to 1 and phase of GSHS, magnitude of GSHS equal to 1 and phase of GSHS is equal to plus minus 180. It means since this point lies on the root locus, so this point will satisfy this condition. It means the phase of GSHS at this point at j root 2 will be plus minus 180. And this is the definition of omega pc. Okay, this is the definition of omega pc. Now let's come here. You know that at this frequency omega pc, at this point, at this omega pc root 2, the phase of gj omega hj omega will become minus 180. So same condition is satisfied here at this point. The phase of GSHS is minus 180. I hope it is clear. Okay. So you can see that at this point, the frequency is root 2. If you are varying the value of k, this frequency will not change. Why? Because this frequency does not depend on k value. Does not depend on k value. If you are varying the k value, then this frequency will not change. This frequency, this will remain at j root 2. The closed loop pole location will change, but the pole on imaginary axis, that will lie always at this point. It means omega pc will remain fixed at root 2. Let's say in this polar plot, I am changing the k value. If you are changing the k value, let's say you are increasing the k value, the polar plot will look like this. If you are increasing the k value, okay, let's say k is not 2, k is 3. If I take k is equal to 3, then the polar plot will look like this. But at this point, the frequency remains as root 2. Why? Because in this system, you can see that it depends on the omega pc depends on phase only. And what is the phase of this function? Phase is minus 90. Now you can calculate the phase of this function. Wait a minute. And you can see that the phase is independent of k. The phase of this function is minus 90 minus 10 inverse of omega by 1 minus 10 inverse of omega by 2. This is the phase. And this has to be minus 180 at omega pc. This phase has to be minus. So if you are varying k, this phase will not change. It means the omega pc will remain at the same point. Now for k equal to 2, let's say this was the polar plot. This was omega pc, that was root 2. Now if I am increasing the k value, then the polar plot will change, and you can see that omega pc will remain the same. Okay, so now from root locus you can say that this point will always tell you about omega pc. If you want to calculate omega pc, then you need to look at this point, the pole location where the system become marginally stable. You have to check the location where the system become marginally stable. So when the pole lies on the imaginary axis, that location will give you omega pc. That's fixed. Okay, that's fixed. I hope it is clear. Okay, I hope it is clear. So this point must be clear first of all. So I found that this is omega pc. From root locus you can calculate omega pc. Now once you get this omega pc, how to get the gain margin? How to get the gain margin? Okay, we need to understand that. We know that from polar plot, when k is 2, let's say, this length is 1 by 3. This length is 1 by 3. And we know that 20 log 1 by 3, 20 log 1 by a, 20 log 1 by a is the gain margin. Now the same thing I want to relate in this root locus. How I can relate this root locus? The same thing in the root locus. Now you can see that in polar plot, if I take k as 6, then this minus k by 6, this point will reach here at this point. Let me redraw the circuit. Let me redraw the diagram. So for k equal to 6, the polar plot will look like this. For k equal to 6, okay. So this is the polar plot for k equal to 6. It means for k equal to 6, system will become marginally stable. It will pass through this minus 1 point, and the system will become marginally stable. Marginally stable, okay. It will become marginally stable. For k equal to 6, the system will pass through minus 1. It will become marginally stable. And for k equal to 2, it is passing through this point. This point is minus 1 by 3. For k equal to 2, this was the graph. For k equal to 6, this was the graph. Now, to calculate gain margin, you can calculate the gain margin from k value itself, from the k value also. How to calculate? 20 log, write the k value here for which the system is marginally stable. For which the system is marginally stable. Divide by k actual. K actual. So you can see that if, let's say, k is 2. For k equal to 2, let's say you want to calculate gain margin. So what you can do is, we know that for k equal to 6, the system will become marginally stable. So you can write k equal to 6 here. And the actual value of k given as 2. So you can put it 2 here. So the gain margin will be 20 log 3. Simple. Okay. It means gain margin, you don't need to calculate gain margin only from A. I mean, A is fine. Using A, you can calculate the gain margin. But there is one more method to find the gain margin. And that method is, if you know for what value of k the system is marginally stable. If you know that value, So we know that for this system, let's say k is given as 2. And when we know that in this system, if k is equal to 6, the system will become marginally stable. Okay, the system will become marginally stable for k equal to 6 for this system. We know that. And the actual value given as 2. And if you want to calculate the gain margin, then you can calculate the gain margin like this: 20 log the k value for which the system is marginally stable divided by the k value which is given as which is actual value. Okay, using this formula also you can calculate the gain margin. You'll get the same answer. You can see that you will get 20 log 3. Previously also you are getting 20 log 3 if k is 2. Okay, it means you should know for what value of the k system is marginally stable and what is the actual value given. Now let's come to the previous question. Now look at the root locus. So for this root locus, it is given that for k equal to 6, the system is marginally stable. You got this value of k. We know that for k equal to 6, the system is marginally stable and the actual value of k is given as 2. So you can apply the same rule here. So gain margin will be 20 log k for which the system is marginally stable divided by the actual value of k. So it will become 20 log 3. Simple. It means in root locus, what you need to do is you need to calculate the value of k for which the system become marginally stable. Okay, calculate this at this point. What is the value of k? Calculate that value. Once you get this value, then look at the actual value given and then you can easily calculate the gain margin. I hope it is clear. Let's come to the next question. Let's say I want to take some different question. Let's say the GSHS is given as, or GSHS is not mentioned. Let's say GSHS is not mentioned. Okay, wait a minute. Let's say GSHS is not mentioned. Only the root locus is provided to you. Let's say this is the root locus which is provided to us. Okay, this is the root locus which is provided to us. And now I am assuming that this point is at -10 and this point is at -20 and this point is 0. Okay, now it is given. Let's say it is given and the root locus is given like this. Okay, this is the root locus, guys. Or let's assume that these points are not provided to us. These pole locations are not provided to us. They are hidden. Okay, they are not provided. Let's call it P1 and P2. Okay, let's call this is P1 and this is P2. They are unknown. They are unknown. GSHS is given as k divided by s into s plus P1 into s plus P2. Okay, at this point k is given as 40. At this point k is given as 40. Okay, it is mentioned that at this point k is given as 40. For k equal to 10, find gain margin. Find gain margin. So in this diagram, these things are provided to you and this GSHS is also provided to you. We need to find the gain margin. Okay, how to calculate the gain margin, guys? It's very simple. What this root locus is saying to you? This root locus says that, this root locus tells us that for k equal to 40, the system is marginally stable. It means we got the k for which the system is marginally stable and the actual value of k is given as 10. So the gain margin, directly you can write the gain margin, that is 20 log 40 by 10, that is 20 log 4. 20 log 4 dB. Okay, I hope it is clear. I hope it is clear. 20 log 4 dB. This is the gain margin. Okay, everyone tell me. I hope you got the idea. It means this type of question may come into your exam. Now many students are thinking that we should plot the polar plot of this function. Now if you are going in polar plot, then it will be very difficult for you. Why it is difficult? Let's say you want to do the polar plot. Okay, so if you want to make the polar plot will look like this. It's a type 1 system and order 3. This will be my polar plot. Now the problem is P1 and P2 are unknown to us. P1 and P2 are not known to us. Now the problem is we don't know this length A. How to calculate this magnitude A? If P1 and P2 are unknown, then how to calculate this frequency and how to calculate this magnitude? This is the main problem here. Okay, this is the main problem here. I hope you got the idea. Okay, so using polar plot, it's difficult to I mean, you can solve, there is some manipulation you can do in polar plot also, but using root locus, you can directly calculate the gain margin. I hope it's clear for everyone. Okay. Okay. For non-minimum phase system also, gain margin is 20 log 1 by A. Actually, yes. Gain margin, I will tell you about non-minimum phase system. Don't worry. I'll tell you about for gain margin, I'll tell you about non-minimum phase system also. Actually, this formula is correct. But for non-minimum phase system, you have to think in a different way. Okay. I'll tell you how. But first, come to root locus only. First, you have to focus on the root locus. How I can use the root locus to find the gain margin. This is important. Okay. So I told you, and I have taken one question also. I have designed one question also where you can calculate the gain margin directly from root locus. Now, it might be possible that root locus is given in a different way. And that different way, let's take a different way. What I can do is I can remove this diagram for the time being. Let's remove it. Okay. Let's remove this diagram and let's design a new root locus. Okay. Now what I'm doing is I am taking a new root locus. Let's say the root locus is provided like this. Let's say the root locus is given like this. So there are 2 poles here and 1 pole here. Okay. So for GSHS, I don't know what is GSHS. 2 poles are at this location and 1 pole is lying at this location. Let's call it P1. This is P1 conjugate and this is P2. So actually there are 3 poles. Now the root locus is provided to us. This will be the part of root locus, and here the root locus is given like this. This is the root locus which is provided to us, and at this point K value is given as 10. At this point K value is given for K equal to 10, the system is marginally stable. It is mentioned to you. And this is the point which is written as J10, let's say. At this point, the location of the pole is J10. For K equal to 10, these 2 poles will lie at these 2 points, J10 and minus J10. Okay? And it is mentioned in the question. It is mentioned in the question. Now, what is given is, for K equal to 5, find gain margin. Find gain margin. We need to calculate the gain margin. Find omega PC, phase crossover frequency. We need to calculate the phase crossover frequency also. Okay, now phase crossover frequency can be known from this point only. This point itself will tell you about the phase crossover frequency. So omega PC is 10 and gain margin is equal to, tell me guys, gain margin equal to 20 log K, for which the system is marginally stable, is 10 and the actual value of K is 5. So 10 by 5. 20 log 10 by 5. So 20 log 10 by 5 is 20 log 2. Okay, so it will become 20 log 2 dB. This is my gain margin. Directly you can calculate this. Okay, now let's say I'm also giving you the polar plot. If I'm giving you the polar plot also, I don't know how the polar plot will look like, but I think the polar plot will look like somewhat like this. I don't know whether it's true or not. I'm assuming that the polar plot is like this. Okay, let's assume that the polar plot is like this. I'm not sure whether polar plot is like this or not. Okay, but let's assume that the polar plot is like this. Okay, maybe somewhat other. Okay, let's say polar plot is given like this. Now this is the point. At this point, the frequency is given as 10. This is my omega PC. It is given as 10. This point is given as minus 1. What is this length A? Tell me guys, find A. Find A in the polar plot. Okay, how to find A? Now I'm not sure whether the polar plot will look like this or not. It may be different. I'm not plotting the polar plot. Actually, I'm not. I don't know whether the polar plot will look like this or not. But let me show. Let's not go into that concept how the polar plot will look like. But I'm sure in the polar plot, I'm sure that this point will represent omega PC. So omega PC has to be 10. Now, what is this length? I need to calculate this length. What is this length, everyone? Can you tell me what is this length? Yes. We know that the gain margin of the system is like this. It means this gain margin has to be 20 log 1 by A. Now by comparing this from the root locus, I have calculated the gain margin. Now we know that the gain margin can also be written from the polar plot. And from the polar plot, the gain margin has to be 20 log 1 by A. Now I can compare these two things and I can calculate A value. So A has to be 1 by 2. This length has to be 1 by 2. Okay, I hope it is clear. So the question is, now let's come to the original question. Let's come to the original question. Let's say I'm erasing this. Let's say I'm erasing this, okay? Now you will appreciate. Let's say the root locus is provided to us. The root locus is provided to us, okay? For k equal to 5, polar plot is shown. For k equal to 5, polar plot is shown. This is the polar plot which is given. Find A. Find A. Okay, the polar plot is given. We need to calculate the value of A, gain margin. So we need to calculate the value of A and gain margin. Okay, this is the question that we need to solve. So I have designed a brand new question for you. A root locus is provided to you. For some GS, just root locus is given like this. And the polar plot is given like this. For GSHS, Gj omega, Hj omega. Okay, the polar plot is given like. So we need to calculate this A value. And we need to calculate the gain margin. So gain margin is 20 log 1 by A, obviously. 20 log 1 by A. This is my gain margin. It means we need to calculate A value for that. Now, how to calculate this A value? You are not sure. So what you can do is, using this root locus, you can calculate the value of A. Using root locus, you can calculate the value of A. Okay? The root locus is provided to us. Now, how to calculate the value of A? We know that from the root locus, we can calculate the gain margin. For k equal to 10, the system is marginally stable. For k equal to 10, the system is marginally stable. It is given in the question. And the actual value of k is 5. So what you can do is, this gain margin can be written as 20 log 10 by 5, that is 2. So by comparing these two, I can calculate, this is the gain margin. So we found the gain margin from the root locus, and I have calculated the A value also. A will be equal to 1 by 2. Okay, A will be equal to 1 by 2. So you can see that how important this understanding is. How much important this understanding is. So from root locus also, you can calculate the gain margin, and then you can come to polar plot also. I mean, I can merge the questions. So you can see these two questions are very important. So I have framed some new question for you. I hope you will appreciate these questions. Okay. Now let's come to the next thing. Rohan is asking, for multiple phase crossover frequencies, how to calculate the gain margin. Yes. Let's say there is a system for which the polar plot is like this. Okay. Let's say the system for which the polar plot is like this. Now we know that this is the phase crossover frequency. Okay, this is the omega PC, this is omega PC, this is omega PC. Let's call it omega PC1, omega PC2, and this is omega PC3. Now let's say your -1 is lying here. It means your system is unstable, let's say. I mean, I'm not sure, but let's say it's given, or maybe you can say that, -1 is lying here. You can take anything, okay? Let's say the -1 is lying here. And this point is k by 5. This point is, let's say, k by 10 minus k by 5 minus k by 10. This point is minus k by 20. Let's say these points are provided to us. And let's say this point is A, B, C, D. Okay. So I'm varying the k value. If you are varying the k value, these points will vary. Okay. If I'm varying the k value, these points will vary. And it is given that if k is greater than 5, if k is greater than 5, less than infinity. If k is greater than 5, less than infinity, system is unstable. System is unstable. If k is less than 5 and if k is wait a minute, k is less than 10, greater than 5, k is greater than 5, okay, then the system will become wait a minute, okay, let's say that the k range is provided to us for the stable or unstable region. Okay, how to calculate the k range for stable and unstable region? Let's say for this particular diagram, it is given that the system is stable. Okay, it is given that the closed loop system is stable. Let's say it is mentioned to you. Find, and k is given as let's say 2. For k equal to 2, this point will be at minus 2 by 5, this point will be at minus 2 by 10, this point will be at minus 2 by 10, minus 2 by 20. And it is given that the system is stable. Now we need to calculate the gain margin. Find the gain margin. How to calculate the gain margin? Gain margin is the margin so that the system remains stable. How much k you can increase such that the system remains stable. Now you can see that k is given as 2 and the system is stable. It means this point will be at minus 2 by 5. And in particular condition, the system is stable. Now let's say I'm increasing the k value. Obviously, when k is 5, when k will become 5, the system will become marginally stable. You can see that it will pass through this. It will pass through this. It will pass through this. This will become minus 1 by 2. It will become minus 1 by 2. Okay. So you can see that this graph will change if I'm increasing, if I'm taking k as 5. For k equal to 5, the system is becoming marginally stable. And this particular system, this yellow color system, is given as for k equal to 2. And for k equal to 2, system is stable. It is mentioned in the question. How much k I can increase so that the system remains stable? Obviously, you can increase the k value up to 5, because at 5 the system will become marginally stable. So now the gain margin is 20 log the k for which the system becoming marginally stable divided by the actual value of k. You can directly calculate the gain margin like this. Okay, you can directly calculate the gain. I mean, you need to understand the meaning of gain margin. Don't go with the formula. Try to understand the meaning of gain margin. Let's say the system is stable. How much k you can increase such that, how much times the k you can increase such that the system remains stable. So you can see that if I am increasing the k up to 5, then this point will exactly lie at this minus 1 point. The system will become marginally stable. If you further increase the value of k, it will become unstable, because this minus 1 will lie inside the, I mean, there will be some encirclement and it may become unstable. Let's assume that the system will become unstable if I'm increasing the k value beyond 5. At k equal to 5, system is becoming marginal. So what is the bandwidth you have? Not bandwidth, what is the range you have? So you can see that the particular value of k is 2 and you can increase up to 5. So how much times you can increase? 5 upon 2.5 times you can increase the k value. So gain margin will be 20 log 5 by 2. It's very simple. So this is the case for multiple phase crossover frequency. I hope you got the point. If you have understood the meaning of meaning of gain margin, it will be very simple for you to understand. Okay. So this was the case, guys. This was the session. I hope you understood how to calculate the gain margin from root locus. Now we have part 2 also. In part 2, which is on tomorrow, I will take the phase margin also. How to calculate phase margin from root locus. Okay. Because I have told you how to calculate gain margin. Now we will discuss about phase margin. Okay. So we will tackle the phase margin concept in the next class, and we also take some questions. Okay. So that's all for today's session. I hope you enjoyed, and see you tomorrow. Take care, guys. Thank you, and don't forget to like this session and subscribe our channel. Okay, and press the bell icon so that you get the notification. There is one more thing I want to tell you, and that is we have our mobile app. So install this mobile app go to the Google Play Store, and there also I'm taking some free sessions, so you can enjoy those sessions also, guys. So don't forget to install our mobile app. Okay, that's all for today's session. Thank you and see you tomorrow. Take care. Bye.